Chapter 12, Number 11. Four masses are positioned at the corners of a rectangle as indicated in the figure. A. Find the magnitude and direction of the net force acting on a 2 kilogram mass. And B. How do your answers to part A change, if at all, if all sides of the rectangle are doubled in length? And we can actually answer B first. Since all the distances would be twice as large, then the factor of r squared would become 1/4. So all of the forces will become 1/4 as large, so the total force will be 1/4 as large, but the direction will not change. I'm going to give everybody names, so let's take this guy and call him Object 1, and call this guy Object 2, and this guy Object 3, which leads to no surprise that this one will be Object 4. And the reason for doing that is that we know that, for instance, Object 1 will pull on Object 2 this way at some strength, and Object 3 will pull on Object 2 that way, and finally Object 4 will pull on Object 2 all on the diagonal. And we'll get those three individual forces, which then we'll have to add in a vector sense, but we'll get them first. So we have that F1 is going to be G M1 M2 over R1 squared, where we can call this R1, which I'm going to leave G as G for the moment, and then we'll have 1 kilogram times 2 kilograms over, I'm actually going to call that distance, let's call that distance 2s, and call this distance s, so 2s squared. So I get something like 2g over 4s squared, or 1/2 g over s squared. I just don't feel like carrying a lot of weird numbers yet. We can plug in numbers for that. We know that we're in kilograms if we plug in correctly, and we'll get newtons, but I just don't feel like tracking lots of units for things I'm going to have to multiply out later anyway. Likewise, we can say that F3 is G M3 M2 over s square, so that's that distance s square. So G times 3 times 2 over s square, or 6g over s squared, which tells us that it's actually considerably larger. It's 4 times larger. It's 12 times larger, because it is both closer and much more massive. And then, likewise, we can say that F4 is G M4 M2 over, and I gotta figure out what that distance is, but that distance would be s squared plus 2s squared. The distance would then be square rooted, but then we're going to square it because we want r squared. So after all of those games, we have g times 4 times 2 over s squared plus 4s squared. And so we get something like 8/5 g over s squared. And again, we can get numbers for that pretty easily, and we will, but I want to just carry them that way, so that we can simplify our math. And we also see their relative strength. This one is somewhat larger because it's a lot more mass, but it's also considerably further away compared to Object 1. So now we're going to have to do, unfortunately, vector addition to get the net force, which would be F1 vector plus F3 vector plus F4 vector. Now, F1 and F3 are both relatively easy because they point along either the, let's define our axes to make life easy. So I'm going to define my axes a little unusually and call that plus x and that plus y. So sort of an inverted axis to our usual, just because things are already pointing in that direction, and that way I don't get extra minus signs. But F4 is going to be annoying because F4 is not going to be either in the x hat or y hat direction. In other words, what I'm saying is F1 is the magnitude of F1 times x hat by construction, and F3 is the magnitude of F3 times y hat by construction. But F4 is a bit of a mess, because F4 is going to be something like F4 with some cosine, let's say, in the x, and F4 with some sine in the y. And I need to be a little more careful to find my angles and stuff like that. So I'm going to say, I'm going to measure that angle as that angle. And then, so I'm really saying I have this part and then that part. So this is way back to chapter 3 stuff. But there we go. And there's sort of a useful thing that we can look at, because what we know is that this is s and this is 2s, and we already found that that was square root 5 of s, because it's 1 square plus 2 square, because that's the other thing square. So the cosine of that angle, which is the adjacent over the hypotenuse, would be 2 over root 5. And the sine of that angle would be the opposite over the hypotenuse, or 1 over root 5. So that allows me to say that f4 as a vector is 2 over root 5 times f4 in the x direction, plus 1 over root 5 times s4 in the y direction. Is that really, really helpful? Actually, yeah, it's going to go a long way towards getting us done. So now we have that the net force is going to be, remember, F1, which we just said was F1 in the x hat direction, so 1/2 g over s squared in the x hat, plus F3, which is given to us by that thing. So we'll have 6g over s squared in the y hat direction, plus the more complicated thing for f4, which is 2 over root 5 times 8/5 g over s squared in the x hat direction, plus 1 over root 5 times 8/5 g over s squared in the y hat direction. And believe it or not, now it's just a matter of getting numbers together. So we might say in the x hat direction we get, what can we do here? Not particularly prettiness, but we have, well, we can pull a g over s squared out of everybody, so let's do that. Notice that that's in every term. And then we have 1/2 plus 16 over 5 root 5 in the x hat, plus, and here we have 6 plus 8 over the 5 root 5 in the y hat. If you plug in and grind out all those numbers, you get 1.3 times 10 to the minus 8 newtons in the x hat, and 4.5 times 10 to the minus 8 newtons in the y hat, which is not quite our answer, of course, because sadly they asked for the magnitude and direction, and we have the components. So we're not quite done. We have to now go back and get those two things, but they're pretty easy from here on out. So now what we have for our net force is that it goes over at 1.3 times 10 to the minus 8, and it goes down at 4.5 times 10 to the minus 8. And what we want is this length and that angle. So the length is relatively easy. It's the hypotenuse of a right triangle, so it's going to be the square root of the sum of the squares. Square rooted, which turns out to be 4.7 times 10 to the minus 8 newtons. And then phi, which is less obvious, but we can go anywhere we want. So we'll say the tangent of phi is going to be the opposite over the adjacent. So 4.5 times 10 to the minus 8 over 1.3 times 10 to the minus 8, which means phi is the inverse tangent of that ratio. The minus 8's cancel out, and that gives us 73.8 degrees. Well, really 74 degrees, since we definitely don't have 3 digits accuracy. Of course, if you had chosen a different angle, you'd have gotten a different number, but it should turn out geometrically to be this.